So imagine an AI system, right? One that plays just absolutely superhuman poker.
Oh, yeah. The kind that completely crushes human prose.
Exactly. But imagine that it's fundamentally throttled. Like the only thing holding it back isn't brain power. It's just the frustrating bottleneck of having to read its own map step by step.
It calculates the odds perfectly, but it's basically trapped.
Yeah, navigating this branching maze of decisions one by one. So today's deep dive is into a state-of-the-art foundational paper in generative AI.
Right, from researchers Juho Kim and Tuomas Sandholm over at Carnegie Mellon University.
And our mission today is to explore how a massive breakthrough in AI game solving didn't actually come from a new algorithm.
No, not at all. It came from taking an old algorithm and entirely changing the mathematical language it speaks. I mean, they unlocked computational speeds up to, like, 4 orders of magnitude faster.
10,000 times faster, which is just wild. So it should address the listener here. I mean, by the end of this deep dive, you're going to look at complex problem solving entirely differently.
Absolutely. Because you'll realize that sometimes the key to moving faster isn't a bigger engine. It's just, looking at the problem from a totally different geometric angle.
So to appreciate the solution, we first have to understand the specific AI engine we are trying to speed up and why it was stalling in the first place.
Right. We need to talk about CFR.
Counterfactual regret minimization.
Exactly. Which is the foundational algorithm for solving large, imperfect information games.
Imperfect information meaning like games where you don't know everything, like poker.
Yeah, poker is the classic example.
Yeah.
And CFR is historically huge. It powered those landmark superhuman AI agents, Libratus and Cepheus.
The ones that basically conquered Heads Up No Limit and Limit Texas Hold'em.
Right. And the way it works is it has the AI play millions of hands against itself.
It's nonstop training.
Nonstop. And after every hand, it looks back at its past decisions and calculates how much it, regrets not taking a different action.
Right, so if it folded, it calculates the counterfactual reality where it, say, called or raised instead.
Exactly. And it updates its internal probabilities based on that regret. Over enough iterations, it converges on a totally unexploitable strategy.
But there's a structural problem here, isn't there?
A massive one. Because general AI, like the stuff powering big language models, relies heavily on parallel computing, splitting massive data sets.
But game theory algorithms are different.
Very. They've historically been stuck in sequential serial execution. Because a game like poker isn't a flat list of data. It's a tree.
A branching sequence of events.
Right. I bet. That opens a branch.
Yep.
You call that opens another. The board deals a new card.
Boom. Dozens more branches.
Exactly. And to update all those regrets, the algorithm has to traverse this entire structure sequentially.
Okay, let's unpack this. Because when I think of modern AI, I naturally assume massive parallel computing.
Oh, for sure. Thousands of GPUs crunching petabytes of data at once.
Right, but standard CFR is basically like a person trying to navigate a massive family tree by tracing every single branch with their finger, one at a time.
That's a really good way to put it.
It doesn't matter how fast your finger moves. You're strictly bound to one path at a moment in time.
And researchers have tried to fix this before, like with Cepheus. They tried to parallelize it by splitting the game tree.
How did that work?
Well, they created a trunk for the early decisions and then handed off the subgames to different compute nodes.
But let me guess. Traffic jam.
A massive one. The compute nodes would just hang around waiting for other nodes to finish their math. It was horribly inefficient.
Which brings me to the obvious question. If AI, like ChatGPT, already uses parallel computing on GPUs, why couldn't researchers just plug this poker-playing algorithm into a GPU and call it a day?
This raises an important question, and it really gets to the heart of hardware architecture. You have to understand tree-form sequential decision processes.
TFSDPs.
Right. A game tree is a TFSDP, and standard code for traversing these trees relies heavily on complex control flow statements.
Like conditional logic.
Exactly. If the player raises, then process this branch. Otherwise, process that branch. CPUs are great at this context-heavy logic.
Because they're designed for predicting branches and switching context.
Yeah. But GPUs operate on a completely different philosophy. They consist of thousands of smaller cores that want to do one simple thing millions of times simultaneously.
So they hate if-then statements.
They despise them. If one core in a GPU cluster needs to process an if and another needs to process the then, the entire cluster breaks down. They just sit idle.
Waiting for each other.
Right. It's an architecture issue, not a hardware power issue. So you can't force a GPU to efficiently trace a branching tree.
The researchers at CMU had to realize this was a dead end.
They did. They realized they had to, melt the tree down and pour it into a shape the GPU inherently understands.
Which brings us to the linguistic shift.
Exactly. Turning trees into spreadsheets. They reframed sequence forms CFR as a series of linear algebra operations.
Okay, wait, hold on. If a GPU hates if-then statements, how does turning a game tree into a grid of numbers actually tell the computer what to do?
Well, the mechanics rely on what are called logic matrices.
Logic matrices.
Yeah, it's a matrix filled entirely with just zeros and ones. And it converts data from a per-sequence representation to a per-node representation.
I think I'm missing the leap between a spreadsheet of numbers and a dynamic branching decision.
Think about the basic property of multiplication. If you multiply your current game data by this matrix, anything multiplied by 0.
Vanishes entirely.
Right. And anything multiplied by 1 passes through unchanged.
Oh, wow. So the multiplication actually replaces the conditional logic.
You're filtering the data rather than navigating it. The researchers were inspired by a framework called GraphELAs.
GraphLace?
Yeah, it treats a top-down or bottom-up tree traversal exactly like multiplying a level graph's adjacency matrix by a vector.
Here's where it gets really interesting. It's like comparing logic matrices to a universal translator.
The universal translator.
Yeah, like it converts step-by-step maze navigation into a flat spreadsheet calculation, and the GPU can crunch that all at once.
That's exactly what's happening. The zeros naturally erase all the dead ends.
But wait, if you're tracking every possible poker hand in a massive matrix, doesn't that take up an impossible amount of memory?
You would think so, but no. The space complexity remains exactly the same as the standard method.
Really? How is that possible?
It's linear space. Big O of the absolute value of P, where P is the number of nodes.
Okay, so it doesn't take up more memory than normal.
Right. Because the matrix is incredibly sparse. It's mostly empty space, represented by zeros. It just organizes the data into a format thousands of GPU cores can crunch simultaneously.
Okay, but does this mean we are fundamentally changing the game being played, or just how the computer reads the rules?
What's fascinating here is that the sequence form CFR running on the GPU produces the exact identical iterates as classical CFR.
So the math doesn't change the game at all?
Not even slightly. It doesn't allow us to solve infinitely larger games because we're still bound by memory limits. It just entirely changes the speed of execution.
Okay, but theory is beautiful, right?
Right.
A radical mathematical translation is only as good as its real-world benchmarking.
Absolutely. You have to test it against the reigning champions.
So how did it actually perform?
Well, they built a custom GPU implementation and tested it against Google DeepMind's highly optimized OpenSpiel CPU implementations.
And OpenSpiel is the gold standard, right?
Yeah. They tested against both the Python and C++ versions of OpenSpiel across 7 different test games.
What were the games?
Coon Poker, Leduc Poker, Liar's Dice, and 4 variants of Battleship.
Tiny, small, medium, and large battleship.
Exactly. And the results are fascinating because of the paradox of the small game.
The paradox of the small game. I like that. What happened with Coon Poker?
So Coon Poker is a tiny game, only 58 nodes, and the GPU is actually 360 times slower than the C++ CPU version.
360 times slower. So what does this all mean? Why did it fail so badly on a small game?
It's the overhead. To run linear algebra on a GPU, you have to transfer the data across the PCIe bus from system memory to the graphics card.
Oh, I get it. It's like chartering a massive Boeing 747 just to travel to the grocery store down the street.
Exactly. The time spent boarding.
Which is the GPU overhead.
Right. The boarding takes way longer than the trip itself.
A regular CPU is just going to hop in a car and beat you there every time.
Exactly. But as the games grow, the speed up becomes exponential. This is the triumph of scale.
What happens when we look at large battleship?
Large Battleship has over 52 million nodes, and the parallelized GPU version was 4,100 times faster than C++ Bernie.
Wait, 4,100 times faster?
Yes, and nearly 19,000 times faster than Python.
That is insane. Computations that used to take days are dropping to minutes.
It really is. And the reason for this is how the depth of the operation scales. It scales as big O of k times the log of b.
Okay, let's break down that math for a second.
So k is the height of the game tree, the number of sequential moves. And b is the branching factor, how many choices you have at any point.
So as the matrices get massive, the GPU overhead becomes completely worth it.
Exactly. The sheer volume of simultaneous multiplication just swallows that initial boarding time of the 747.
Once it's in the air, nothing can touch its speed.
Precisely. And this framework isn't just for vanilla CFR.
Right, let's talk about the ripple effect on future AI research.
The paper proves it easily adapts to state-of-the-art tabular variants, too.
Like CFR plus SPICE, which Cepheus used.
Yes. And discounted CFR, which lets the AI forget bad early strategies, and predictive CFR++.
So it works with all the cutting-edge tools, but let me push back a little here.
Sure.
If this doesn't magically let us solve games that are 100 times larger because of memory constraints, is this really a breakthrough or just a really impressive stopwatch trick?
If we connect this to the bigger picture, you have to realize that in research, speed is innovation.
Speed is innovation. How so?
When your iteration time drops from weeks to mere minutes, researchers can test thousands of hyperparameter combinations overnight.
Right. They aren't scared to fail anymore.
Exactly. They can test entirely new hypotheses that they previously would have abandoned simply because they couldn't justify the compute time.
That completely changes the daily reality of an AI developer.
And it has huge practical applications. Think about games played in a repeated setting with slight variations.
Like poker, where the action depth constantly changes based on chip stack sizes.
Right. If your AI takes weeks to calculate a strategy, it can't adapt. If it takes minutes, you have a highly responsive agent adjusting in real time.
So to recap the journey for you today, we started with an AI system fundamentally bottlenecked by its own architecture.
Trapped reading a massive branching family tree one node at a time.
Right. And the biggest leaps in technology don't always require inventing a brand new engine.
Sometimes it's just about realizing your old engine runs 10,000 times faster if you translate its instructions into a different mathematical language.
Turning trees into spreadsheets, conditional logic into linear algebra. And the next time you face a massive bottleneck, the solution might just require a change in perspective.
Exactly. You might just need to speak the computer's native language.
Which leaves me with one final provocative thought for you to explore on your own.
Oh, I love these. Let's hear it.
If translating game theory into linear algebra unlocked a 4000x speedup by simply speaking the computer's native language, what other incredibly complex human problems are we currently trying to solve step by step, just waiting to be translated into the right mathematical dialect?